Hello, everyone. Okay, let's get started. I don't know if you can hear the music or if I've squiffed something. I'll leave it there and we'll see what happens. I'm not very good with sound levels still. Okay. Today, the plan is to have a rummage around and see if we can fix Alien Abacus. At the end of last session, we also looked at Puzzle 2, which wasn't solving. I've been back in the archive, and Puzzle 2 is a finned X-Wing, which we have not implemented, and that's why it doesn't work. So I'm not going to worry about the fact that Puzzle 2 isn't solvable, but I will include a comment to explain that. At the behest of a colleague and friend, I am going to be trying to not use VS Code this time. So I'll be using an editor called Helix. So let's very quickly come in and say that, you know, why Puzzle 1 doesn't work. So this, if we want, is going to be a finned X-Wing. And again, if we... Now, how do I extend to end of line in Helix? Because I'm used to Vim, you see, when I'm editing in a terminal. But I'm being convinced to try to use this. So how do I extend to end of line? Is it capital X? Nope. Is it F $? Nope. You see, today is going to be full of these difficulties. Is it just going to be like if I press F end? Nope. Select extend. Accessed by typing V. Select mode echoes normal mode but changes any movements to extend selections. Ah. So if I find end of line. So if I go V end C, there we go. Aha, you see I'm learning. To do Puzzle 2 requires finned X-Wings. When we implement those, we can enable this. Okay, and if we explain why Puzzle 2 isn't solving. Right, so we can move on now to what we actually want to solve, which is the fact that Alien Abacus doesn't work. So let's open Kaji rules, rules cell pairs. Okay, so let's pop back to Alien Abacus for a moment and remember what was going on. So if you remember, when we asked this to solve, the difficulty we had basically is in understanding this grouping of cells. So if we switch into solving mode for a moment, what happens very quickly is that the system works out that 1, 2, 3, 4, and 6 are valid here, which leaves this as a hidden 5. And it leaves that as 1, 2, 3, 4, 6. And it does similarly down here, giving us a hidden 5 here, but then it gets stuck. And the reason it gets stuck is because our solver now can't understand that we can't put 3 and 6 here. And if we step through this in the setter, then the way that this happens is that we start to come on, get there. There we go. We get this sort of thing. Placing a 3 forces a 6, which causes a contradiction. We don't have any contradiction support in our solver, and right now I'm not sure quite what I would do to do a contradiction, but I did have a thought, and my thought was this: if we, in our cell pair solver, we effectively say, I know that's a pair, and I know that's a pair, and they're in all 3 of these cells share a region, in this context the row, or I could do it there, and in this context the box. But either way, I can now think about this cell. And the reason I can think about that cell is because I know that these 2 are in the same region, therefore any forcing that this cell does needs to leave these 2 being different. Otherwise, it can't solve. So if we think about it again, if we just take these 3 cells as being the set that we're going to consider, and they're 1, 2, 3, 4, and 6. Yeah? What we ought to be able to do is say, okay, if this cell is a 1, then this cell must be a 2, and now this cell cannot be filled because this cell must be a 2, and these are not different, which allows us to eliminate 1 from there. We can then say, okay, well, what if this is a 2? If this is a 2, then this cell can be 2 or 4, sorry, it can be 1 or 4, and this cell can be 1 or 4. That's 2 things that they can both be, so that's okay. So we can leave 2. Then we can say, well, what if it's a 3? In that case, both of those would have to be 6. That can't be done. So that can't be a 3. What happens if it's a 4? Well, if it's a 4, then both of these would have to be a 2. And that doesn't work, so it can't be a 4. Can it be a 6? Well, both of those would have to be 3, so it can't be a 6. And that therefore eliminates us all the way down to a 2, which leaves those being unable to be 2, unable to be 3, unable to be 6. So we've got a 1, 4, and a 2. And so here we have now, because that's become a 5, we have this as a hidden pair of a 3, 6. That 2 means that that's a 1 or a 4. And then, you know, we have our constraint here. If this was 1, this would have to be 2. If this is 4, it could be 3, or it could be 5. But there's a 2 and there's a 5 in the row, so that becomes a 3, which forces that to be, forces that to be the 4, which forces that to be the 1, and so, and that gets us our solution. So this is my plan. My plan is to look for 2 pairs such that one of the cells is shared and the other 2 cells share a region. Or we might even say those 2 cells see each other. So that's that's the goal of what we're going to aim to try and find. So let's see if we can write something to discover these pairs first of all. So I thought that the cell pairs rule was probably the right place to do it, and we can do that here by looking for all of these groupings of cell pairs. And I'm only going to do the positive assertions for now. Later, if we decide to, we might move down and consider every cell pair within the system. Okay, so what we want to do is we want to say for each cell pair in our relationships. So we're going to do that. Cell A, cell B, rel in. So doing that same loop again, only what we want to do now is we want to actually try to pair these things up. So can I do that by dint of something else on self.rel? So can I go for thingy in self.rels.iter dot and now my hope is that there'll be something in iter tools where I can do maybe tuple combinations. Yes, that's what I want. Tuple combinations. And if we think about it, this is going to be first and second. And these are now horrendously long inlays. So I'll just do that temporarily, although I'm pretty sure that the moment I save, that will reformat. But this gives us a start. So do first and second have a singular overlap. How do we test that? Well, if first.0 equals second.0 and first.1 does not equal second.1, there's one way of overlapping. And you see, I'm going to struggle with this. So what we're going to do very briefly is just say if either way round they overlap, then we're good. And are we going to get fully overlapped relationship pairs? We might. I'm also going to require that they're the same relationship for now. Is that fair to do? XVs, Vs and Xs. I don't think it matters that they're the same relationship. I think it just matters that they have two cells that are the same and they have two cells that are different. Can I do first.0.min? No. Do we have ORD on cell index? This is a question that I have. And I think what I can do for that is I can pull up the workspace symbol picker and get cell index. We don't have ORD, we do have EQ. If I stick ORD on cell index, then this would enable me to very quickly spin them around for checking. I'm going to stick partial ORD on them. So first.0.min first.1. Do we think that's possible? Can I say let that happen? We get an error, which is that min exists for cell index, but its trait bounds were not satisfied. Go to diagnostic. Cell index ORD. Okay, so min requires ORD, not just partial ORD. So that means that we can do that. So let's actually try to do this neatly. So we can go if first.0.min first.1 is equal to second.0.min second.1, then we have an overlap. And in fact, if that is not the case, we do not have an overlap. Right. So we now know that we have an overlap. We're not sure which way round, but the second thing that we want to do is verify that we're not identical. So first.0.max first.1 is equal to second.0.max second.1. We are fully overlapped. So we continue again. So now we know that we have an overlap, and so what we can do is we can create some sort of conjoined constraint if and only if the other cells happen to share a region. Right, how are we going to achieve that? The overlapped cell, we need to know, but we can achieve that later. So, what are we going to do? Goodness me, my brain is not turned on. Let overlap equal because we knew we had an overlap and we knew we weren't doubly overlapped. So the overlap no. Okay, now we've created our overlap. Next, what we want to do is we want to build like a double cell pair constraint where we tell the cell pair constraint, we tell that the overlap. So we're going to go builder add constraint double cell pair constraint. First up routes, there we go. Now obviously double cell pair constraint doesn't exist, so let's go ahead and create that. That is going to require us to come to the constraints. So we have a cell pair constraint and we're going to add a double cell pair constraint. Pub struct double. Cell A is a cell index. Cell B is a cell index. Rel AB is a cell pair relationship. And neg AB is a bool. Cell C is a cell index. Cell D is a cell index. Rel CD. And neg CD. And the overlap is also a cell index. I mean, that's a big chunk, but you know, import. I do wish that Rust Analyzer at this point would start to recommend that it could fill all of the rest of this out. Assert cell A equals overlap or cell B equals overlap. Right. And then we can just do so that's trivially created the relationship, and then we can do import constraint for double cell pair constraint. Missing members difficulty. This is going to be medium at this point, I think. What did we say? We said medium plus 1,000, so a double cell pair relationship is probably medium plus 1,500. Prepping the board, nothing to do for now. Okay. We actually need to go in here. And bring that through as well. Import it. And now it's expecting overlap. Right, so that's created our double cell pairs. What we could do here is in prep board, we couldeprintln that. And now we will see that there is a double cell constraint that's been created. Just the one, which is a bit weird. Which doesn't make sense. There should be way more of these double cell pair constraints created. Yes, I mean, these are all the combinations that we could be considering. So let's change this line. Select first, change second. Whoa. See, we're getting somewhere. Cell index doesn't implement display, of course, so let's just stick the debugs on there. And this time, you know, we can see, okay, well, that really should have been a pair. Because first's max equals second's min. Oh, rude word. Okay, so my theory here that we could do it in this fashion is wrong. All we can do is say good God. I really don't want to do this with a set, but I'm too lazy at this point. So this is our, we have an overlap. So if not any of that, no overlap. Continue. How about now? See, now we have a whole bunch of double cell pair constraints. That makes a lot more sense. Good. So instead of doing nothing, let's do a logical step. This time we want the state. So our logical step is to constrain the two halves of oh no, before we even do this, we've computed that there's an overlap, but we haven't computed that the cells are all in the same region. Now, I don't want to say that the overlap is in the same region. I want to say the other is in the same region. So I'm going to have if first.0 is overlap, so other A is going to be first.0 is overlap first.1, else first.0. This is going to be a B. and that to be. And now what we're going to do is we want to know that A and B have overlapping, have a region in common, which is of a suitable size. So let's get all of the non-overlappy regions. Builder. Do we not have builder.regions? We do, apparently. Maybe. No method named regions found for puzzle builder in current scope. So here's our puzzle builder. We have region, which gives us the region objects. But we don't have give me all the region IDs. So it's going to be self.regions. No, it's just going to be 0 to self.regions.len. Dot map given n region ID n So we have all of the regions, and now all we want to do is find out whether or not the regions contain the others. So regions.iter.copied.any are such that cells is region is builder region R dot to cells contains other A and contains other B. If not, no overlap found. Continue. Right. So we still have double pair constraints, but compared to above, we've only got a few. So we have this one, which is two differences that are chained through cell 31. Let's do the ratios, because here are the ratio chains. And let's see if we can identify where they are. Because what we should have is, if we go 0, 1, 2, 3, 4, 5, 6, 7, 8. So 7 and 8 with 2 and 8 overlap is 8. 7 and 8 with 9 and 8 overlap is 8. Yep. So those are the two in row 2. And those are the two overlaps in row 5. Good. Let's keep going. So first of all, what we want to do is, so essentially we have relationship AB and relationship CD. We need to determine a limitation based on the overlap such that the other cells cannot be satisfied. Then we can eliminate such. So step 1, we need to know all the values that the overlap cell can have. State.cell values. So that's all the values that the overlap can have. What we now want to do is determine which of A or B is the overlap. Perhaps we can do this computation in the new. So rather than storing all of A, B, and overlap, we can store cell AB we can store rel AB, we can store neg AB, and we can store inv AB. We can store cell CD, rel CD, neg CD, inv CD, and we can store overlap. And our goal here is to determine which of cell A or B is not the overlap. So cell AB is, if overlap is cell A, cell B, else cell A. Cell CD is if overlap cell C, cell D, else cell C. And we're missing whether or not we are inverting. And inversions in this context, let's say that we compute the value of the overlap. So what we're doing is we're looking to see, is there anything in the in cell AB. So we're looking then to narrow the values of cell AB based on what is satisfied. And we need to know whether we have to invert ordered comparisons. So normally what we would do is we would say, if the relationship is satisfied between A and B, where what we need to do is we need to say between overlap and AB, and then we need to do an invert. How are we going to do that? No, I don't like this change that I've done. Let's go all the way back to where we were. And let's think. So, the first thing we want to do is compute all of the values for A, B, C, and D. and we'll collect them as a vector. So we've collected up all the values A, B, C, and D. We now want to do the relevant constraining based on the overlap cell. So let values AB equals if cell A is overlap, then what we want, because cell A is the overlap, we want all the possible values. No. Oh, goodness me. What do I want to do here? I mean, one of A and AB is equal to one of CD because it's the overlap cell. And what we want to do is we want to say for each value that the overlap can have, we want to try and do our constraint and check. So let's actually be a little bit more sort of constrainy here. Give me 1 sec. Apologies, drink acquired. So, for each value that the overlap cell can be, we want to look for our constraints. So, because I'm not even interested in trying to be clever here, we're going to go for overlap value in state.cell values self overlap. So our goal here is, given this value, what constraints can we make in AB? So let permitted AB equals if cell A, then what we want is we're going to say we want values B iter filter given the cell's value. What we want to do is we're going to go, how did we do it up here? Self.rel.satisfied value A, value B, X or neg. Right. So that is going to be self.relab.satisfied. So we want the value in A, which is the overlap value, or the value in B, which is v.value. Else we want values A, iter, filter. So this is going to be self.rel AB satisfied with v.value and overlap value.value XOR self.neg AB collected as a vector. Right, so that gets us our values that are permitted to be in AB, whichever one that is. And we're going to go permitted CD is the same. So if overlap is self cell C, values D, self.rel CD dot satisfied by overlap value v value XOR self.neg CD collect vec else and then here that D should be a C. So we've got our permitted CD. Right. So our final goal here is that we need the union of AB and CD to have at least two values, neither of which are overlap value. But I think that's fair because the relationship thing means they're not going to be the same. So, is it worth saying collect as a vector? I don't think it is. I think we should just say collect and we're going to say that these are in fact no, we're going to let them be vectors just for what do you call it, open close collect vec. What have I fluffed? Oh, for some reason there's an extra close print there that shouldn't be there. I will get used to Helix eventually. That makes more sense, and it's not if overlap, it's if self.overlap. Unused variables, yep, that's all fine. Okay, so our goal here is there must be at least one member of permitted AB not in permitted CD, or vice versa. If not, permitted AB given ABV, permitted CD contains ABV. Sorry, not map. That should be that should be all. So if all of permitted AB is contained within permitted CD and permitted CD, all CDV permitted AB contains CDV, effectively the same sets. So this is our case. So eliminate what is it? Overlap value from the overlap cell. Right. So how do we get the name of the constraint here? Right. That's the entire constraint name. And so let's yank that. Let's paste it there. So this time though, it's rel AB, neg AB between cells A and B, pushstra and rel neg between this is going to be CD, CD. Eliminates, right, push symbols over some overlap value dot symbols 0. State symbol that push from push cells So now actually need to do the elimination. And if we remember from before, We do state.eliminate for the overlap, the symbol. And then we can go if state.eliminate self.overlap overlap value symbols 0 dot changed. So we actually succeeded in doing the elimination. Return action. What's the likelihood that will work? Errors. No implementation for cell value is equal to cell value. I mean, that's fair. We'll probably need to do that. Go to definition. How do I do that? No, it's not that. That's actions. It's just GD. So cell value is going to have partial EQ. And now we can solve it. Hooray! So, those ratios gave us a hidden single. The difference did that. Those ratios did those eliminations, gave us a hidden singles. The differences did that. Now, we haven't formatted our thing quite right. I need a space there. So here's a paired instance. So paired difference of 1 between row 5 column 2 and row 6 column 2. Difference of 1. And difference of 1 between row 6 column 2 and row 6 column 3 eliminates 5 from row 6 column 2. Let's just have a quick look at what that is. So that's 5262, 6263. 5262, 6263. There we go. It ended up saying that if that was a 5, we wouldn't be able to fill those. Presumably 4, 6, for whatever reason, is not available. Probably because there's a 4 in there as a tuple. And so it was unable to do that. And it kept going, and it kept going, and it kept going. Depressingly, that paired action was the only one that was necessary to actually solve the puzzle, and the solutions did match. So we can be reasonably confident that this is the right implementation of this, just not necessarily solving it in the way that we thought it was going to go. But that's fair enough. You know, if we change the difficulty here, so we say that it's actually easier to do it with a paired than it is to do it on its own, then what happens? Now we panic. That's not good. Something went wrong. Collection regions. Paired difference of 1 here. Eliminated 6. Then it eliminated 5. Then it eliminated 4. Then it eliminated 3. Then it eliminated 2. Then there was a naked single 1. And then it tried to eliminate 1. And that went wrong. That's fair. So something really weird went on there that we're going to need to investigate before we can call this good. So eliminating 6 makes sense. It eliminated 6 because if it was 6, then both of... So if that was 6, both of those would have to be 5, which would break. So then it went on and eliminated 5, which doesn't make sense because those could be 4, 6. So we need to work out why that happened. So let's go here and we'll say, okay, so we have an elimination. Yeah? And the elimination means that permitted AB and permitted CD did not have an overlap. Boom. So the first time out, that makes sense because the only things that they can be are 5 and 5. It's just not allowed. Difference of one. This time out, we said that these two, so symbol ID 5 value 6 and symbol ID 3 value 4, did not match symbol ID 5 value 6 and symbol ID 3 value 4. Oh no, they're both the same. Oh, they're both the same, but their length is at least 2. That was the mistake we made. Okay, so here we've said that they're all the same, but what we can do here is we can say so if they're all the same and permitted AB.len is 1. Yeah. In fact, is less than 2. So that no longer causes a problem despite doing more of these paired eliminations where possible. So let's just get rid of that extra debugging for a moment. And have a look. So what have we got? So the difference of 1 eliminates 6 and 1, and 6 and 1. That makes sense. So this means this can't be 1 or 6. So that's 2, 3, 4, 5. And it's done the same there, 2, 3, 4, 5. Difference of 1 and ratio of 2 eliminates 1 from row 2, column 4. So here, it said, well, if that was a 1, then both that and that would have to be a 2. And that doesn't work. So it eliminates 1 from there. That's fair. It then says that the row 2, column 2, row 2, column 3, row 1, column 3, row 2, column 3 ratio eliminates 6. So it's now said that grouping eliminated 6 from there. It eliminated 5, it eliminated 4, it eliminated 3, and it eliminated 1. Which means that that ended up being a 2. Naked single 2. It did that same thing and got a naked single 2 down there. And so we eventually rolled out. So let's pop that back up to 1500 and do a cargo run. And we're getting the operations we need, which is good. And so here we got the paired difference eliminated 1, paired difference eliminated 1, paired difference and ratio eliminated 1. Paired ratio and ratio eliminated 6. We got hidden single 6, and we repeat, and we can make our way out. Good. I believe that more. So what have we added to Kaji? We've made cell index orderable, and we've added the ability to extract regions and compare cell values. So Kaji add ord to cell index, partial EQ to cell value, and regions to puzzle builder. And I should really be somewhat more polite with this. So let's do that. And that's all going in Kaji. Add double pair relationship constraint. Okay, so now Alien Abacus can be solved. Let's just very quickly add that to the tests. And do a cargo test. And we're good. Right. What is the next thing that we need to try to do? Let's have a think. Next constraint, F puzzles. Let's have a look. Thermometer could plausibly be implemented as a set of paired pairs, which might be interesting. Palindrome we've done. Renban, more complex. Whispers are minimum differences. Not sure I like those today. Entropics and modulars. Ditto, region sum lines. And no. Anything to do with summing, I'm a little bit leery of right now. I mean, I don't think we actually did the minimum, and maximum. If you remember, we set out last time to do fortress cells. I don't think we actually did them. So let me first of all try to find an example puzzle of that. Please give me a few minutes. Okay. I think I have found a puzzle. It's a 9 by 9. So let's start a fresh Sudoku. It is a maximum. And it looks like this. And we're going to have to write the puzzle loader for this, by the way, because we haven't yet. That's a 6, that's a 1. That's a 6, that's a 2. That's a 4, that's a 9. 3 and 7, 2 and 9, 2 and 4. So in theory, that should solve. And it does, but it's horrendous. Y-wing hinging, big, lots of contradiction type situations. I'm not sure that we're going to do a terribly good job of this, but we can certainly try. So I'm not convinced that this is going to be particularly easy for us to do. And this is by Sudoku today. We could try some other shapes though, just in case. So again, it's a maximum constraint. Which is quite a fun shape. 5 and 2, 9 and 3, 4, 7, 7 and a 2. Still taking ages, which means it's doing contradictions, which I don't particularly want. Let me see if I can find an easier Fortress Sudoku. Let's try this one. This is only a 6 by 6. And the rules again are digits in shaded cells must be higher than orthogonally unshaded cells. Two, 4, 3, 4, 6, 3. That's fascinating. So I know where to place a 2 in box 4. That's fair. That's because I've transcribed it slightly incorrectly. Reason being that step 1, we need to reshape the regions. The regions are in fact that shape. Now let's have a go. That's much faster. That's all naked singles. Although, of course, that when it says it's a naked single, it's doing that because it knows that given the 6 is there, that has to be 1, 2, 3 or 5, and only 5 is greater than 4. So it is doing the pairwise operation. So let's grab that. Let's create the solution. Let's rename it to Fortress Sudoku by Fun with Puzzles. And I'll stick the URL in there just so that we don't lose it. Just go again, save the solution, clear the puzzle, and let's grab its code. I call this Fortress Maximum because it's a maximum fortress. And then let's come back to the tree and have a look. So the maximum is a list of individual cells. And remember our rule here, if we get rid of the JSON thing, our rule, so let's say we're considering this maximum cell, is that it gets a relationship with its orthogonal cells only if its orthogonal cells aren't also a maximum or a minimum. And I think, sorry, only if its orthogonal cell is not a maximum. So for example, if there were an X relationship, let me just run the solve. Unfortunately, we don't have like a 4-6 pair, but in theory, if I put an X relationship there, that would still matter. So it's only maxima pairs that we don't want when we set up the logic when we load the puzzle. So let's clear that again, and let's come back to our puzzle. Right. Close that, close that, close that, close that. Open. Here. Step 1, let's actually load our new puzzle. And what did we call our new puzzle? We called it Fortress Maximum. Of course, that fails to solve because we haven't actually loaded the maximum. Oh, goodness me. Find, convert. We want the fpuzzles conversion. XV pairs, difference pairs, ratio pairs. For maximum in val.maximum. And let's load here because we need to have vec of f puzzles single cell. Is that what I called it? Yep, f puzzles single cell. And I'm going to assume it's called minimum, but I'll just double check by popping over, sticking a minimum cell in and checking the JSON. Yes, it's called minimum. So that does the load. Now we need to do the conversion. So we have our fpuzzle single cell. And we actually need to compute the orthogonal cells for that, or we need to insert it into the rules so that the orthogonal cells can be computed later. We don't have access to the grid at this point, so we can't do the orthogonal cells. So I would like our puzzle data so that our grid rules, as well as having pair relationships, is going to have maximum and it's going to have minimum. So those are the maximum minimum cell locations, which we can then extend into our thing during our load. Go previous. Grid rules mute. Maximum push. Maximum cell row. Maximum cell column. And for minimum, inval.minimum. So that's done the conversion. And now we need to find the Sudoku rules, because here's where we generate all of our cell pair rules, and we need to add to our positive relationships all of our other cell pairs. So positive relationships have been computed from there. So we need to get the orthogonal cells. So we need to go, for row call in raw rules maximum iter copied. Cell is going to be row -1 col -1. And now we need all of the orthogonal cells to that, which is going to be builder dot all orthogonal pairs. This takes a list of cell indices to give orthogonal pairs to. Fine. She's going to take a borrow list cell. And we're just going to go for ortho cell in. No, this is wrong. Add region, add interference, cells, orthogonal pairs. So all orthogonal pairs is all of the orthogonal pairs for the list of cells that we give it. What I want is all of the cells that are orthogonal to the cell that we tell it. So pub fn orthogonal orthogonal cells self doopy-doo. Right, so all we want to do is we want to go for each offset. We want to take the current cell's row and column. So this is going to be let cell info equals self.cell info cell. Row is cell info row. Col is cell info col. For row offset, column offset, in offset. O row is row offset. O col is col offset. Not a vector, it's a hash set. And then this is just going to be ret.into iter. Right. So orthogonal cells given a cell index tells us the cells that are orthogonally adjacent to it. So it's not for ortho cell in that, it's orthogonal cells cell. If tell you what we're going to do now. We're going to do the conversion first. So we're going to go raw rules minimum iter copied map given row and column rows row -1 col -1 collect as hash set. Cannot find hash set in scope. Import it. Good. Let's repeat that. Maximum raw rules maximum iter copied given a row and a column rows row -1 col -1 collect as a hash set. So again, we've collected them up, and now all we're going to do is we're going to go, you know, for cell in minimum for other in builder dot orthogonal cells cell if not minimum dot contains other Let mute minimax is an empty vector. Minimax dot push cell other cell pair relationship colon less than. So in a minimum case, the cell we have should be less than the other cell. And then we can go for cell in maximum for other in builder orthogonal cells. Cell if not maximum dot contains other minimax push other cell pair relationship less than, and then it's posrels dot chain minimax. And now it can solve. So just to just reiterate that. So what we've done is we've converted the minimum cells and maximum cells into sets. We then create an empty vector into which we're going to push the cell pair relationships that represent the minimum and maximum relationships. And then we just iterate through the orthogonal cells and verify that they don't contain one another, and then feed the relationship in. So that should be good. Yeah, that's added Fortress. It's added all of the other bits and bobs that we need. So let's have a quick look. What have we got? So Kaji, we've now added an orthogonal cells. So this is Puzzle Builder orthogonal cells. So Kaji rules puzzle data. And there's some nasty mess. Don't like that. Slightly surprised that cargo format didn't get rid of that. May have to see if Helix can be configured to do so. But for now, that's fine. So this is Kaji rules, add minimum, maximum to puzzle data and Sudoku rules. Kaji loader, add minimum and maximum to F puzzles loader. And now finally, we're going to want to have just double check that all works. Add Fortress maximum. Test. Okay, and I mean, the maximum and the minimum, they're just the same things back and front, so there's no point in worrying about what each of those could be. if we come back very briefly to F puzzles, we now know that we can do the diagonals, we can do anti-knight and anti-king, we can do disjoint groups, and we can do non-consecutive. We know that we can do extra regions, odd and even, palindrome, difference ratio clone, minimum maximum, XV, negative ratio, negative XV, and quadruple. I fear that next time we're going to have to start thinking either about some of the more complicated line types like thermometers, and we might have a go representing thermometers purely as chains of cell pairs, just to see what happens. Or we may have to look at some of the operations that actually involve performing mathematics, like summing things for killer cages or little killers, that kind of thing. But I think I'm probably going to call it there for the night. So just to confirm I have pushed, I have. Thank you all for watching, and I will see you next time.